Okay, students, this is Mr. Ferris, and I'm going to walk through Lesson 9.2. This is the lesson where we learn all the official steps of a one-proportion z-test, which just happens to be the first hypothesis test that we have conducted, top to finish, with all the steps, all the things you need to get points on the AP exam, and which is basically all the things you need to have a complete answer as well. The problem I'm going to present is about quiet dice, and you may not even know what quiet dice are because we've been not in person that much, and I usually, when we have a dice activity, I get out these dice that are made out of foam, so they're very quiet. They don't make noise like the heavy ones do. And students have told me that they do not believe that these foam dice, these quiet dice, are actually fair. We are going to see if it is or not. Normally I would roll this in class and we would collect real data, but I will be going off of data that I collected in a previous class. So what we're interested in is the true proportion of times that the dice comes up a certain number. Now we'll just have to pick a number. Hopefully we pick well. When I did this a while back, we picked 5. And so when I rolled the die 68 times, I got 15 times that the die came up a 5. So if we were going to write just the initial data, our sample proportion would be that 15 times out of 68 rolls, we got a 5. And that is a little on the high side. If you do the calculation, it's 0.221. And we might wonder if it's a really fair die then, because it's supposed to come up 1/6 of the time, which is about 16.6 repeating. And it came up 22.1, which is a little high. So once again, the question is it high enough to be weird and suspicious that maybe 5s come up more than 1/6 of the time? Or could a 5 have come up 22% of the time, even if the die was fair, and we don't, do we have evidence against fairness or not? But we're going to formalize it. We're going to formalize it in what's called a hypothesis test. So the first step usually is to write the hypotheses. And we have practiced that already in lesson 9.1. The null hypothesis is always kind of the default. If nothing weird's going on, if there's nothing wrong, then the probability or the percentage of time that a 5 would come up would be 1/6 of the time, which is 0.16 repeating. If this is not a fair die, we have to pretend we didn't really look at the data yet, because before we look at the data, we would have found the die to be unfair if it was too many times coming up 5 or not enough times coming up 5. So what would concern us if it's just not 1/6? It will be an unfair die if it comes up less often than it should, or if it comes up more often than it should. So that's why it becomes what we call a two-tailed test. It becomes a not equal to alternative hypothesis. Now, it just turned out that our data happened to be higher, but we would have been just as concerned if it came out to be like 10% 5s instead of 16. So ahead of time, we make this decision that we're going to go with a not equal to. And then, of course, we finish this by saying what we think, or defining what P is. So where P is and I think it's always good to say the word true, just to make sure we are talking about the population parameter, where P is the true percent 5s on this quiet dice. I only rolled 1 die. So I can't really say that it is true for all quiet die. I really just took 68 rolls of a single die. We could have designed it differently. We could have rolled 5 or 6 different die until we got 68. But still, we could only apply our findings then to the die that we rolled. Second step is usually the conditions. And the good news is it's the same conditions that we've had for a one proportion interval. So if you can remember the 3 conditions, first of all, we'd like to have a random sample. Well, this is a little different because we only rolled it 68 times out of all the times we could have rolled it. It's not really a random sample because we didn't take a sample from the rolls that could have been made tomorrow or next week or next year. So what we might say is something like this. We assume the 68 rolls were representative. That would be a nice way to say it. We know they're not random. It's not really a random sample. We'll assume the rolls were representative of all possible rolls. Kind of getting sloppy here. Representative of all possible rolls. I suppose we just say of this die. So as long as they're representative, we can move on and believe we've got a good sample. And then secondly, surely 68 rolls is less than 10% of all rolls. And that's basically because you could roll this thing an infinite number of times. So the population of rolls is infinite, in theory. And then we want to check the large counts condition, make sure that we can use a normal model for the sampling distribution. And that comes down to, do we have enough successes and failures? That's what we would check for a confidence interval. Well, we can do better than that because we actually have a true p. We have a p equals 1/6. We have a hypothesis, so we're going to check 68 times 1/6 and 68 times 5/6. So n times p and n times 1 minus p. In this case, 68 times 1/6 is 11.3, and 68 times 5/6 is 56.6. And they are both greater than 10, so we know our sample size is big enough to use a normal model for the sampling distribution. So this is where we want to probably say, it's a good place to say, we will proceed with, just as a habit, the name of this test. This is called a 1 proportion, and you can abbreviate that, a 1 proportion Z test. That is the name of this procedure. This is the third of many procedures we will learn this year. So this is number 3. And believe it or not, all that stuff under number 2 is just worth 1 point, typically on an AP test. A lot of conditions and the name of the test. All right, so because we believe we can use a normal model, let me go ahead and draw what that would look like. Let's say we've got a normal model for the sampling distribution. So we believe, because of condition number 3, that all the p-hats, had we gathered them all, would pile up in a relatively normal way. And according to what we learned in Chapter 7, the mean of all the p-hats, remember this is all the theoretical p-hats that we could possibly grab using the same sample size, same procedures. So of all these p-hats, one of them turned out to be the one we got, which was 22%. But the mean is going to be the true proportion, which is 0.16 repeating. That was our 1/6 from our null hypothesis. And the one we got was 22%. It's out here, 0.221. And we would like to know the probability of landing as far as we did, or even farther, if the null hypothesis was actually true. So if we were going to shade in, let's say, the area that we're concerned about, we want to know what's the probability of getting a sample proportion of 22.1%, or even worse, even more extreme, if the null was actually 0.16 repeating. Now here's something that's kind of weird. It's I guess something you have to just think about. Back here when we wrote the hypotheses, we said to ourselves that we will be surprised if the sample proportion is too low, and we will be surprised if it's too high. That's what we're concerned about. To not be a fair die, that means one of the numbers either comes up way less than it should or way more than it should. So we were already going to reject the null hypothesis if the p-hat was too low or too high. So here's what we have to consider when we're drawing this picture. When we're drawing this picture, we have to consider the possibility that, yes, we could have landed out here, which is actually where we did. We landed a little on the high side. But we could have landed on the low side, and we would have rejected down here too. So when we calculate the p-value, we're going to also calculate this area, which of course will be identical to the one on the right side. And both of these added up are going to be the p-value for this problem. And it all goes back to the fact that back here, when we first decided what the alternative was going to be, we decided that we were going to consider numbers that were too extreme below and numbers that were too extreme above. And so we were automatically doing a two-tailed test. And what that means mathematically then is that we have to do a p-value that includes both of those. So the next thing that we calculate is the area. What's the area of that? And one of the things that we have to write down for credit, typically, is something called the z-test statistic. The z-test statistic. We would like to know what the z-score is for this p-hat boundary that we got when we got a sample of, what was it, 15 out of 68. So that 22% that we got for p-hat landed to the right of the mean a little bit. And the z-test statistic is simply the z-score for the p-hat that we got. It's the z-score for 22.1.221. And that's something called the z-test statistic, and that is something we have to write down and we have to show. We have to compute that and we have to show what it is. So we have to get out our calculator and calculate essentially a z-score. This is going to be a z-score for the place where we landed. In other words, the boundary where we landed. We have to calculate the z-score for that. So let me write out what it is. I'm trying to show you all the steps just so that you know all the things that are going on behind the scenes. So the z-test statistic is really just a z-score. So if you go back to chapter, what was it, chapter 2, I think it was, when we learned about z-scores, you calculate a z-score by first finding out how far away from the mean you are. So the formula would be, we would take our p-hat, that's where we landed, and we would subtract the mean of our distribution, which is p, and then we would divide by the standard deviation for this sampling distribution, which actually we call it the standard, we usually call it the standard error with confidence intervals, but we are going to use the standard deviation because we know p. We have p. So we're going to use p. We're going to use the formula p times 1 minus p over n. And this is the z-score formula that we used back in chapter 2. But it's a little more complicated because of the three things that we use. The denominator especially is kind of complicated because it's a formula. So our p-hat was 22.1%. Our true proportion is 16.6%, repeating. And then the denominator is going to be p. I'll go to fractions here just to make it easier to write. P times 1 minus p all over our sample size of 68. So this number, when we calculate it, is going to be the z-test statistic. Now, the good news is we could type this all in our calculator and it would be wonderful and we'd feel really good about that. But it turns out we just have to report that number, and there's a much easier way to report that number by simply using our graphing calculators. So if we do the one proportion z-test on our graphing calculators, we will find that it will be something the calculator produces for us. So this is probably a good time to do that, is let our calculators take over and do the z-test statistic. So on a graphing calculator, what we're going to do is go to the tests, so stat, and then over to tests on our graphing calculator. And we want to find the name of this procedure, which is a one prop z-test. On my calculator, it's number 5. I think it is on yours too. So if you go to one prop z-test on a graphing calculator and type in all the particulars, all the things that we have to type in, you'll notice the first thing it asks for is the p sub 0. P sub 0 is the proportion that we used back here in the null hypothesis. So the calculator calls it p sub 0, and we're going to type in 1/6. That would be the easiest thing to type in. We could type in the decimal, but then that would be rounded, and we don't want to use that. And then it's asking for x and n. X and n are simply the numerator and denominator of our p-hat. So x is 15, and n is 68. And then the fourth decision is what type of null or what type of alternative hypothesis did we write down? Your options are not equal to, less than, or greater than. So all you do is go back and look at the sign that we used, or I should say the symbol that we used in the alternative hypothesis, and it was not equal to, so we will select that first option, and then tell the calculator to calculate it. And in an instant, it comes up with a z-test statistic of 1.193, if you round a little bit. That is the z-test statistic. And then right underneath that, it says P is 0.2328. Well, that plain P is actually the p-value. It's the area of those two tails. And it did add them up, because when you said not equal to, it knows that there's two of them, and so it adds up both tails. And it gave us a p-value of basically, we could call that 23% and be good. 23%. So we can use our calculator to do the heavy lifting, and in fact, to be fully transparent with you, I will just tell you this, that on an AP test, you really do not have to have this, and you do not have to have this. On an AP test, they're really just going to look for the z-test statistic and the p-value. Those are the two things you must have written down for credit. So all that other stuff was just kind of background to show you where it came from, because of course it could come up on a multiple choice question. These formula types of answers do tend to come up on multiple choice questions. So even though you don't need it for credit on the AP test on a free response, it's very possible you would need that for credit on an AP test in the multiple choice section. So there we have it. That's the third step. There's only one more step, and that would be the conclusion. And I did not realize I was writing so big, so I don't have a whole lot of room here, but I think I can squeeze it in. There's basically three things you have to write for the conclusion. And as a reminder, I'm going to put LCD. That used to stand for least common denominator, but in statistics, that means you need to have linkage, you have to have context, and you have to have a decision. The linkage is why you're making your decision, and that goes back to the p-value. The p-value is fairly high. There's a 23% chance that we would get a sample proportion this weird, this unusual, and that's not really very unlikely. 23% of the time, you could get something that is this far off from 1/6. So we do not have any evidence to suggest that the die is not fair. But we have to link it to our p-value. You have to say why you make the conclusion. We have to talk about dice, that's the context, and then we have to make a decision. Do you reject the null or do you not reject the null? So here's how I'm going to have you write these, and this is the way we're going to write them all the rest of the year. We're going to say something like because, this is our linkage, because the p-value, and that was 23%. I'm going to write right over the printing. Because the p-value is greater than any reasonable alpha level. Now I'll have to look at the problem if they gave us an alpha level, and I don't believe we had an alpha level. A good alpha level to use is 5%. So I would always just default to 5% if they don't tell you what it is. Because the p-value is way bigger than an alpha level of 5%, we cannot reject, or the book likes to say we fail to reject HO, the null hypothesis. That takes care of two of those two things. We took care of the linkage. It's because the p-value is larger than the alpha level. And we took care of the decision. We failed to reject the null hypothesis. What we have not written yet is the context. The context also serves as kind of a, I guess you would call it a common sense answer to this, because most people reading that sentence I just wrote have no idea what I just said. What in the world did we fail to reject, and what does that mean? That's like a double negative. What this means is we have, in this case, no convincing evidence. We have no convincing evidence that the proportion of 5s on this die is not 1/6. All right, so this doesn't sound like the best English in the world to have a double negative, because we're saying we don't have evidence that it's not 1/6. That's like saying in the court of law when you say not guilty, well, they don't have evidence that they're, that they committed the crime. And it's kind of a double negative. But that's the right answer. That is what we're saying. We don't have any evidence to reject the null. We have no evidence that it's unfair. That's another sentence that you could say if you wanted to have a third one. You could say, and this means that we have no evidence that the die is not fair. So again, we didn't prove that the die is fair. We just have no evidence that it's not. And those are not the same thing. Because what if the die actually, instead of being 16.6 repeating, maybe that die regularly is 18%. 18% of the time it comes up as a 5. That could be. All we know for sure is that we don't have evidence to say it's not 1/6. We have no evidence that it's not fair. But we cannot say with any certainty what exactly the true proportion is. We just know we have no evidence that it's not 1/6. So that right there are the 4 steps, written a little on the large side. We probably could have squeezed it in a little better. But these are the 4 steps that we always want to take. There's a lot of little pieces in here. And I told you about the work. The work is really kind of optional. If you are going for a free response question, that's probably optional. We do still want to put the Z in front of this. But we still want to know how that comes about because of multiple choice questions. So that's one problem. And what I would like you to do now, we're going back to this potato chip problem that we talked about in the previous lesson. And now you have an opportunity to actually conduct a complete test. And so you've got the whole page there. I would like you to see if you can kind of follow the steps. This time it's just a one-sided test because it just says greater than. They don't worry about if there's less than 8% blemished. What they worry about is if there's more than 8% blemished. What I'd like you to do is to do that complete hypothesis test, 1, 2, 3, 4, all the way through, and see if you can get the correct conclusion. And I'll just tell you what it is, just so you can end, hopefully, there with the right answer. So let me look at my final answer here. It looks like to me, oh, you know what? Yeah, I always forget this. You have to know what the sample proportion is before you can do anything, and that is not in the problem. It's funny because I forget this every year, and I always have to add it. So let's assume that they took a random sample of 500 potatoes, and they found 49 to be blemished. 49 is 0.098. 0.098. So if they found 49 blemished potatoes out of 500, I would like you to run a hypothesis test on that and see what you come out with. And I will just, what should I do? Let me kind of sort of hide it down here. If you get the right answer, what you'll find out is that the z-test statistic is 1.484, which makes the p-value 0.0689. So that would be a way to check that you did it right, and then I will let you make the right conclusion based on that. So I'd like you to do that first, and then I will have a separate video to tackle the probability of a type 1, type 2 error. So that's all for this part.